to explore the behavior of light. To begin, let's explore how light behaves. I'm going to point the laser to the ceiling. Okay. Any students? Okay. So which way is the laser light traveling?
Straight to the ceiling.
Right, straight up. And where is the dot of light that's produced by the laser right now?
On the ceiling.
All right, good job, guys. Okay. So now I'm going to see, students, how the light interacts with the mirror. And I'm going to hold the mirror parallel to the floor, okay? And students, before we even go any further, I want to talk to you a bit about safety, that we never point a laser in someone's eyes, and I'm going to be shining it indirectly so that it hits the floor or the ceiling. And just heads up for when you get ready to do your investigation. We'll talk safety again there. So I want you to watch, students. I'm going to shine the laser onto the mirror, and I'm going to line the laser up with this line here. And I want you to see where the dot of light goes, and you'll be able to see it on the table, students. Okay, I'm turning on the laser. All right. Okay, so where is the dot of light now?
On the mirror.
Okay, is it anywhere else? Can you see it on the table?
Yeah. It's on the table surface.
All right, okay. Now I want you to notice how the light is traveling from the laser. It's going, I'm shooting it up here, and it's ending up over there. So let's try it at a different angle. Okay? This time I'm going to hold it straight up to the mirror. Students, where do you see the laser light now?
Right below your hand on the table.
So it's going directly up and coming straight down. So why would the light on the laser be in the opposite direction of where I'm shining it?
It's bouncing off the mirror.
You're right. So what's happening to the light as it's hitting the mirror?
It bounces off.
All right, good job, guys. Okay. So what did you notice about how the light hit the mirror when I put it at this angle and came off?
It came off at the same angle that you shined it in at.
You're right. Good job, students. It's exactly what's happening. It's coming in at this angle, it's going off at that angle. Okay, so what is another way that we can say light has bounced off a surface?
It reflected.
And you're right. Good job, students. Reflected. Okay? So everyone say reflected with me.
Reflected.
And we're going to write this word in our journals. And the meaning. Light that bounces off of a surface or material. Make sure you get this in your journal, students. Okay? Okay, so students, can you think of some other examples of materials that reflect light in a similar way that the mirror did?
Water, some shiny materials like aluminum foil, and certain plastics.
All right, good observations, okay? So we've observed then that light strikes a smooth, shiny surface, and it reflects in a pretty predictable manner. So, and how did you say that light travels?
In a straight
In
line?
a straight line. So we know that light can travel in a predictable manner, and it can also, it travels in a straight line. So on your worksheet that I'm going to hand out to you, I'd like you to answer question 1 where you draw an arrow that shows the path that light would travel if it strikes the mirror. And then I would like you to complete questions 2 and 3. Now let's think about light and how it interacted with the mirror. Did the light pass through the mirror?
No.
How do you know?
Because it wasn't behind the mirror.
Good observation. Yeah, so it hit the mirror and it came back, but it didn't go through the mirror. So now, students, I want you to observe this. I've got a cup of water, and it's got, the cup is clear, and we're going to observe what happens when I put the pencil into the water. Okay? So I'm going to hold it up. I'll put the pencil end down. Okay? So, students, what happens to the appearance of the pencil when I put it in the water? Can you see that?
It changes direction, kind of.
Right. Does it look a bit broken too, like it suddenly changes?
Yeah.
Okay. Does the light pass through the cup and the water?
Yes.
How do you know that?
Because we're able to see the pencil and the water.
You're right. You're able to see it. So when light travels through one substance, in this case it's traveling through the air, and then through another substance like the water, the path of light can be bent or refracted. It makes the pencil actually appear like it's broken and its shape has changed. Everyone say this word with me. Everyone say refracted.
Refracted.
Okay? And we're going to also, students, write that word in our journals. And I'm going to write it on the board and you copy it into your journal. Refracted. All right. So, students, can you think of any other examples where you've seen light behave like the light did when it struck the pencil in the cup of water?
When I go swimming in the pool.
All right. Have you ever noticed how your feet kind of look big when you get into the shallow end?
Yeah.
Have you ever played that game where you throw the penny in and someone goes to get it, and then when you go to dive for it, it doesn't look like it's in the same spot? All right, those are both examples of light being refracted. Good job, students. Okay, I want you now to answer the fourth question that's on the worksheet I gave you earlier. And let's talk about this again. When light rays bend and change the direction they're traveling, what is the word we use for that, the science word?
Refraction.
All right, good job. Okay, so today we're going to investigate one of the ways that light behaves when it interacts with other materials. We're going to investigate refraction, and our question of the day is, how does light refract when it's shined into different substances? And you'll be exploring that question in just a few minutes. All right, students, in the investigations you're about to do, each of you will be performing different roles, and we're going to all work together like scientists do. I want you to take 1 minute, and I'm going to walk around the room while you're doing this, and you're going to read your job cards for water and corn syrup and oil. Oh my, you'll get one of these, and you should be reading them out loud to your teammates, and I'll be coming around and checking to make sure that everyone understands their roles. So we've observed two ways that light interacts with materials and other objects. We've observed reflection and refraction. Okay? And you will be doing two investigations. Half the class will do the first investigation, then we'll swap and you'll do the other. But I'm going to go through the directions on both of them with you right now so that you understand what you'll be doing. For the first investigation, we're going to trace the path of light through different liquids. We're going to use corn syrup, we're going to use oil, and we're going to use water. And soon you'll have all these materials out in front of you. And you'll also have this worksheet that looks like this, and it tells you where to put the liquid, and it's got a key where you'll check off whether you're testing the water, the oil, and the corn syrup. And you'll do those in that order. And before you go to the next liquid, you should have completed the first one. There are two places for you to place the laser. You can see it on your worksheet. So you'll do it twice, and what you'll be doing with your partner is the worksheet will be lying down on your table, and your partner will be holding up the target board behind it like I'm doing, and you'll lay the laser down in the position. You'll put the liquid on the position where it says on the worksheet, and you'll shine the laser. And what you'll do is you'll take your pencil and you'll record how the light travels through the liquid. So students, what are we observing and collecting data about in this investigation?
We are shining light through some different liquids and we're tracing the path of the light as it travels through these liquids.
All right, good job. And as we walk around the room and assist you with your investigation, what should we see that you're doing when you're using the laser? How should it be used? That
it's on the mat at all times, and we should not point the laser at anybody's eyes, even our own.
All right, good job. So you know exactly how to use the equipment, okay? On your worksheet, you'll record the path of the light as it travels through different liquids, and you'll put dots on the placemat where the laser light hits the marker. So students, this is your placemat. So as you're observing, you will just put dots to record how the path travels. And you'll be doing that with your pencil. Okay? Does everyone understand what you're going to be doing?
Yep.
Okay? So how will you record the path of the light?
We're going to put dots on the placemat where the laser light hits the marker.
Okay, so you know exactly what to do. Okay? So I want you to think back to when we used the laser for the first time when I first started the lesson and we pointed the ceiling. How did the light travel?
In a straight line.
Okay? And in that case, what was the light traveling through?
Air.
It was traveling through the air. You're right, okay? So we learned that light travels in a straight line, but in this investigation, you're trying to find out if light will still travel in a straight line as it passes through the air and then the liquids, the 3 different liquids, by following the path of the light. So how do you predict the dots will look like on the placemat when it goes through the different liquids?
It will be in a straight line.
So why do you think the dots are still going to be in a straight line or the light will travel that way?
Because that's the way light travels.
Okay, we're going to get to see that. What do you predict the light will do as it travels through the liquid itself?
Go in a straight line.
Go in a straight line, okay, all right. So we're going to do the investigation and see what actually happens as the light travels through the air, the liquid, and then again out on the other side through the air. We'll be shining the laser through each substance one at a time and drawing the path of the light from the laser. You'll have 7 minutes to perform this investigation and record your observations. Does everybody understand what your task is?
Yes.
All right, good job. Okay, so technician, I'd like you to come up and get the tray of materials for your table. You'll be in charge of reading the task card for the group, and the task card will give each member of the team instructions on how to perform the investigation. Once you have your tray and you've read the directions, you can begin. If at any point you don't understand what to do or you need help, raise your hand and one of the teachers will come assist you. Okay, so this is how the investigation using the 3 different liquids is set up. One of the students will be holding the target board. We've kind of taped it up here for demonstration purposes. And you put the liquid, in this case it is the corn syrup. And the laser, it's important to have whatever laser pointing. This one has 2 lights and the laser's in the bottom opening. So the students, first of all, they would record the answers under their predictions. How will the light travel when it enters the substance, and as it's in the substance and after it leaves the substance? That's question 1. And then they make their observations on their worksheet with all 3 of them, and then they'll record the conclusions. So we're going to demonstrate how to do it, and students would be recording their observations. So this is the corn oil, and as you shine the light, you can see how it travels straight and then it begins to converge here, and you can see it on the target. The student then places it on the other side. You can see it again, so they get that X factor going in. Okay. And then we're going to change out the material. This is the oil. Same thing. Students would be recording on their worksheet for the oil. They keep the target board in the same position. And you can see how the light converges a bit there and there. And then we'll do it also with the water. Students would be recording after each one of these on their worksheet. They'll draw it on the worksheet with a dotted line. I have the dots here, but they're drawing it on their worksheet. And again, this is the water. All right, students, now we're ready to begin the next investigation at Station 2. Okay, so with that, you're going to make sure we need to make sure you understand different types of lenses you'll be using: the concave, the convex, and an oblique lens. Okay, so describe to me what the concave lens looks like to you. How would you describe it?
Looks like 2 U's put together.
It's a good way to describe it. Okay, it looks like it kind of scoops in 2 U's. Okay, and now I'm going to hold up a convex lens. How does the convex lens look to you?
Looks like it's bulging out in the middle.
You're right. Looks like it's bulging out. Okay, so how could you tell the difference? How could you differentiate between a convex and a concave lens?
The convex lens looks like it can fit on either side of the concave one.
Good observation. It bulges out. Looks like it could fit in there. Okay? Excellent. Okay? So if we put this together, we call that a special type of lens. It's called an oblique lens. So how can we make an oblique lens?
By putting the 2 lenses together.
Okay. Does it matter which way?
Nope.
Not really. Okay. There we go. Okay, so in this investigation, you're going to see how light travels through these 3 different lenses, and we're going to trace the path, just like we did before in the other investigation. And we're going to trace the path as the light from the laser enters and exits a concave lens, a convex lens, and the 2 lenses put together. Okay? So students, I'm going to explain now how you set up the lenses to do this investigation. So you'll be taking turns at your desk with this. You'll have a placemat that looks like this. It says convex, concave, convex, and oblique. Okay? You'll place the lenses on the placemat, and then you'll be shining the laser through. And again, you're going to be recording the path of the light each time. For the lenses, set up the lens this way, concave. So you'll set up the lens like this. There's 3 places that you set the laser. So 1, 2, 3. Repeat for the convex lens. You kind of adjust it. If you hold it up a bit, you can see it, the lines of it. I'll hold it in 3 different positions. You can see the path of the light. And then for the oblique, together. And here you can see where it travels in a straight line. Let's all say concave together.
Concave.
All right, good job. Okay. So, and this is similar to the lens you used. Okay. The property, because of the property of the shape of this lens, it makes images seem smaller. And an example you might have seen of a concave lens is the peephole on your front door. And if you've ever looked at the peephole, you'll notice how the person outside doesn't look as big, but you can still see them. Now let's take a look at the other lens. What is the shape of this lens?
Convex.
Right, and it's got the bulging out in the middle. That's sort of the opposite of the concave. And I'd like you to copy the definition of the word convex. It's a lens that refracts inward and makes objects appear larger. Okay, make sure you're writing this in your journal. Now let's talk about how the light behaved as it traveled through each of the lenses. How did the light travel through the concave lens?
It was refracted outward.
Okay, all right. So it bent outwards. And just like we wrote in our definition, the light travels outward, making objects appear smaller. Make sure that's in your journal, students. Okay? And on the convex lens, how did the light travel through the convex lens?
It bent inward.
Right. So make sure you have written in your journal that the convex lens is a lens that refracts inward and makes objects appear larger. What is the one thing they had in common?
The light was refracted.
Exactly. Okay. So an example of a convex lens might be in an overhead projector that you've seen in some of your teachers' classrooms. When we're using a convex lens, we say the light converges. It comes together. Okay? And you can hear the V, the converge. If a lens caves in on both sides, what do we call that?
Concave, because it looks like a cave.
And if a lens bulges out and it's thick in the middle, what type of lens is that?
Convex.
All right, good job. How did the paths of the light, when they were shown through each of the lenses, compare?
One made the light go outward, the concave lens, and the other made the light travel inward. Both of them refracted the light.
Right, so they're both objects that can refract light, but the way they refracted it was different. So what directions did the light from the laser point when you used it on the concave lens if you pointed the laser on the right-hand side?
It would go further right.
Okay? And when you placed the 2 lenses together and we made the oblique lens, what did you observe?
The 2 lenses together made the light just goes straight.
Oh, interesting. Okay, so why do you think that was? Why do you think it went straight?
Because the two lenses canceled each other out.
You're right. So it went through one lens, and then the light was converged through the other. So it went outward with the concave, and then the convex lens made it converge again. Okay? All right, students, now that you've mastered figuring out the path of light through different materials, refracting light, it's time to apply your knowledge. So, have any of you ever seen one of these?
I have not.
Okay, well, it's called a kaleidoscope, and it's a tube-shaped optical instrument that's you rotate it to produce symmetrical designs. You have to look through it at this end. So there's two kinds of kaleidoscopes. There's a reflecting kaleidoscope and a refracting kaleidoscope. What do you think a reflecting kaleidoscope has inside the tube?
A mirror or something shining.
Right, a reflecting kaleidoscope will usually have some sort of reflective surface on the inside, lining the inside, and then it usually has some bits of glass or beads inside that move around when you turn it. The mirrors in the kaleidoscope are at an angle, so they produce these symmetrical images from the beads or whatever objects are inside the kaleidoscope. When people mention kaleidoscopes, most people are talking about reflecting kaleidoscopes. However, there are also refracting kaleidoscopes. So how do you think the refracting kaleidoscope differs from the reflecting kaleidoscope?
There's no mirrors and there's no beads.
You're exactly right. They don't have either of those. So we obviously have what kind of kaleidoscope?
Reflecting.
We've got a reflecting, okay? So there's no mirrors on the refracting telescope, but you would still see images in them, okay? So what causes the light to be refracted inside the kaleidoscope?
The glass at the end. The light is bent when it goes through a different medium.
You're exactly right. I don't know if you can notice it, but at the end here there is this material, and the light has to travel through there, and it goes through a different material. As it gets to your eye, you can kind of see that if you look at it up close, and when you get it in your desk, you'll be able to see that. So the light is bent in different ways because the lens at the end of the refracting kaleidoscope is shaped to create this effect. So you remember the straw at the beginning of the lesson? Refraction caused the straw to seem bent because the light rays slowed down when it entered the water. And whenever you see a rainbow after it's rained and the sun is shining, you're seeing an example of refraction there. And that's when the light travels through the raindrops. And the raindrops are behaving like they did with the cups here. They are refracting or bending the light, and we see an effect we call a rainbow. So why do you think scientists stopped using refracting telescopes? Many telescopes are designed with refraction. Think about what refraction does to the image of an object.
Refraction bends light, it would be blurry.
You're right. So now scientists use reflecting telescopes that use a curved mirror to observe the stars in the sky. But before that, they used refracting telescope that used a convex lens to bend the light into focus. Okay, so guys, you've done a really good job today. You've learned a lot about light and how it behaves. We're going to pass out a worksheet to you where you get a chance to show what you know and what you've learned today about light. If you are finished with, when you get finished with the show what you know, you're able to answer the question in your science journal: what are some real life examples of reflection and refraction, and how are they significant?